Hello students. Good morning everyone.
Good morning, sir.
So today we'll start with the new chapter, magnetic energy. See, whenever a current flows, it may be a transport current or atomic current, a magnetic field is produced. Now, magnetic energy is stored in the magnetic flux, that means magnetic field lines. So just like we have electrical energy, there is a magnetic energy. So first what we will do is, we'll calculate the magnetic energy of the coupled circuit. Now here we consider the magnetic circuit. See, I had mentioned in the previous chapter, in the second chapter, what are the magnetic circuit? The magnetic circuits are circuits made from the magnetic flux in a well-defined path. So that is called the magnetic circuit. Now suppose we have electrical circuit, then it produces the magnetic flux. Now suppose there is another circuit in neighborhood of that, then that magnetic flux will fall over the second circuit. Electromagnetic induction will also take place. There will be self-induction as well as the mutual inductance. So EMF will be induced in the first coil as well as EMF is induced in the second coil. So now these two circuits are called as the coupled circuits. Now this coupling is there. See, coupling means like joining together because of the magnetic flux. Now similarly, there can be a third circuit. So the flux from the first and second circuit will fall over the third circuit, and this will get coupled with this. So we can have large number of circuits which are coupled together, held together or joined together by means of a flux. So this circuits, coupled circuits, will possess the magnetic energy, and that we have to calculate. Now to calculate, first of all, see, the magnetic flux is produced by the current, and when you switch on the current, the magnetic flux changes. Magnetic flux changes. It will change over the given circuit, and if there is a neighboring circuit, then the flux will change over that. EMF will be induced. Now, to establish this, see, to produce this flux, some energy is taken from the battery which supplies the current to that circuit. So, some energy is to be spent from the battery to establish the magnetic field. See, the magnetic field is a consequence of the electric current. Electric current is a consequence of the electric battery which is connected to that. Now, suppose this V is an applied voltage. That means the battery voltage. V is the applied voltage, and it will induce EMF small e. So E is the induced EMF, because when you apply the voltage, beside that voltage, what will happen is the current is changed, so flux will change, so EMF will be induced. So that E is the induced EMF, and R is the resistance of the circuit. Then by using Ohm's law, we have like this. See, the total voltage V plus E is a total voltage. And by Ohm's law, total voltage is I into R, current into resistance. Then next what you do is, to this circuit, to this equation, see, this V plus E equal to IR, you multiply by I throughout. So what you get is VI into, see, VI into EI equal to I square R. What you have done here, this we have obtained by multiplying here by current I. And then we write VI equal to this minus EI plus I square R. We take this EI on the other side. Then, to establish this current, work is done by the battery. So work done, see, the work done, dW is the work done. Then by definition, see, the potential difference is work done per unit charge. So the work done is the potential difference into the charge, V into dQ. But we know that I equal to dQ by dt, rate of flow of charges. So dQ equal to I dt. So we have VI into dt. Then we use the Faraday's law. See, what happens is, by Faraday's law, because of this flux is changing over this circuit, EMF is induced, and that is equal to minus d phi by dt. EMF induced is proportional to the rate of change of the flux, so d phi by dt, and minus sign comes due to the Lenz's law. So now here we substitute this I dt, see, this I dt as this E into dt and minus sign, that is d phi. See, from we get from here this in this equation, this I continues here, and minus E dt. So from here, minus E into dt is d phi. Then this V equal to IR, see the second term, look at the second term, V equal to IR, so I square R dt, So now we have written that work done as I d phi plus I square R dt. Now this I square R, see, I square R represents the power dissipated. I square R is a power dissipated because the resistance is there. So whenever in the circuit the current flows, then the heat is generated, it becomes hotter, heat is generated, and that power loss is I square R. Power into time, that is energy. So I square R dt represents that electrical energy which is converted into the heat. Now what happened is, it is irreversible conversion, because that heat generated, we cannot get converted back into the electrical energy. So it is irreversible conversion of the electrical energy. So the second term represents uh, the power dissipation of that circuit, the power which is lost to that circuit, or energy which is lost to the circuit. Then this I d phi, see I d phi, so that there is a change of flux d phi is there. So it represents the work done against the induced EMF. So what happens is, when the EMF is induced by Lenz's law, it will be opposed to the applied voltage. So what happened is, to maintain the current, some work is to be done by the battery. See that current has to flow to the circuit, so work is to be done by the battery. So this I d phi represents work done against the induced EMF. Then normally heat generated in the circuit is very small. See, heat generated is very small, and you can make it small by taking the wires of the proper material. So now what we can do here is, we can neglect this quantity I square R dt. It is negligible. Normally it is negligible. So actually the work done is only against the induced EMF. So this is the work done by external source, that is the battery, that I d phi. So dWb we write. B is the work done by the battery, I d phi. And the second term we have neglected that. Then suppose there are n circuits. See, suppose there are n circuits. N circuits are there. As I mentioned earlier, first circuit, second circuit, third circuit, they are interconnected by means of the flux. So they are coupled. If there are n circuits, then the previous equation we have written dWb equal to I d phi. So the total work done by the battery will be the sum of that. So I1 d phi 1 plus I2 d phi 2 plus I3 d phi 3 and so on. So I equal to 1 to n. So total. Then the flux change produced by the current change in the n circuit themselves is, let us write at d phi I. That flux change produced by the current change in the n circuit, d phi I. So we write that summation j equal to 1 to n d phi ij by dij into dij. So actually it is a summation of d phi ij. So we write in a certain form. So divided by dij into dij. Then this d phi ij by di. So we know that, see, this flux is proportional to the current. Flux is proportional to the current, and that constant of proportionality is called as a mutual inductance, M. Mutual inductance. This you might have studied in your lower class. This is a mutual inductance. So d phi equal to d m di. So this d phi by di equal to m. So we write this as mutual inductance. We write this as mutual inductance Mij. So this we have written Mij. So Mij d phi ij by di. So we get it from phi equal to mi. So d phi equal to mdi. So m equal to d phi by di. So we write it as Mij, because that I circuit is coupled to the J circuit into Ij. So this is phi I. Because we have taken d phi I, we have taken phi I from that. Now let us say that these circuits are rigid and stationary. That means what it means is, see, whenever what happens is current flows, a magnetic field is produced. So then that flux falls over the second coil. So magnetic field is produced in that also, and there may be attraction and repulsion. So what is done here is, we say that the circuits are rigid and stationary. So because of this magnetic field, they are not get attracted or repelled. So somehow they are held at a same position. So there no mechanical work is associated with the change in flux. So the change in flux, there no mechanical work is associated. So no mechanical work is done. So the work done by the battery, see, the work done by the battery dWb is just equal to change in magnetic energy of the system. So because there is no mechanical work which is done, so we write this dWb as equal to du. Du is the magnetic energy of the system. So this magnetic energy of the system is obtained from the work done by the battery to increase the current. Then let us state that instead of all current fluxes be at the same fraction alpha of their final value. So this II is a, let us say II is a final value. In between, II dash is alpha times II. Then flux phi I dash is alpha times phi I. This alpha is that fraction of that final value. So we write here d phi I dash equal to phi I d alpha. So we write here d phi I dash equal to this phi I final value, that is a constant. So d alpha, the fraction will go on changing as the flux has increased. So phi I is the final value. So final value is constant. In between it is a variable. So d phi I dash equal to phi I d alpha. So now we can write this, the magnetic energy of the rigid station circuit as U. See, du equal to dWb. So this U equal to integral of dWb, total energy of all the circuits. Then we substitute here dWb. We substitute here dWb, and then we substitute II dash, and then this constant we take out, I phi I, because there is a final value, it is a constant. So what is there inside is alpha d alpha. Now here we are integrating with respect to alpha. So the limit is from 0 to 1. See, alpha is a fraction. So the total is 1. Fraction, the total is 1 starting from the 0. So when you integrate this, alpha d alpha is alpha square by 2. Then low limit is 0, upper limit is 1, because alpha is the fraction. So if you add all the fractions together, you will get equal to 1. So this we substitute the upper limit 1 square by 2, that is 1 by 2, minus substitute the lower limit, that is 0. So that is 1 by 2. So 1 by 2 is summation of I equal to 1 to n II phi I. And then you substitute here in the equation 3. In the equation 3, substitute that phi I. So what we have done here is, see, this equation half, see, the half summation I equal to 1 to n II phi I, we substitute for phi I. This phi I we substitute this phi I, mij, ij, a summation of that, j equal to 1 to n, that is from the equation 3. Then I have written that what was written in the previous case here. Now here mij equal to mji, because self-inductance of first mutual induction of first coil with the second coil is equal to mutual induction of second coil with respect to the first coil. Mij equal to mji. Now mii, mutual inductance of the coil to itself, that is called as self-inductance. We write it as Li. See, Lii, same circuit, so it is called as the self-inductance. Mij, that is the mutual inductance, because it is the inductance between the two circuits. Now first circuit to second circuit, or second circuit to first circuit, that value is equal. So then what happens is, you can substitute here. If you substitute here half, this you will get L1 half. Suppose if you substitute all these things here, half L1 I1 square plus half L2 I2 square plus half Ln In square. That's for the self-inductance when I equal to J. Then in this part, half is not there because Mij equal to Mji. So the two quantities will join together. See, two quantities will join together. So half plus half is 1. So that's what we get here. And so this is the final expression for the magnetic energy and for the coupled pair of the circuit. So this is for the coupled means a pair of the circuit. Only if the two circuits are there, then what you will get is half L1 I1 square, then M12 I1 I2 and half L2 I2 square. So there are two circuits are there. So this for the two circuits. Then if the single circuit is there, then we have phi equal to Li. This we know. A single circuit, there is no mutual inductance, only self-inductance. So flux is proportional to the current, and the constant of proportionality is the self-inductance. Then energy U equal to half I phi, as we have seen earlier. And when you substitute that phi equal to Li, what we get is half Li square. So these are the expressions for the magnetic energy. This in general for N circuits. See, this is for N circuit. This is for the pair of the circuit. and this is for the single circuit. So this is the magnetic energy stored in the circuit. So I'll hold it here. On the Wednesday, you'll have ISA. So I will send you the question paper and you have to post it back. So detailed instruction will be given. The next lecture I will take on the next Monday. So thank you very much.
Thank you, sir.
Welcome.